A very good day to Dr. Muhammad Hazri. We are from Group 4 of BNF 36103 Section 1. My teammate, I am Lee Seng Ek. My teammate is Tam Jing Shen, Wang Shangla, and Qiu Yiming. Today, we are going to present about convolution encoding. Convolution coding is a widely used coding method which is not based on block of bits but rather the output code bits are determined by logic operation on the present bit in a stream and a small number of previous bits. In the encoder, data bits are input to a shift register of length k called the constraint length. As each bit enters at the left of the register, the previous bit are shifted to the right while the oldest bit in the register is removed. Convolution encode in digital communication system. The diagram on the left shows the digital communication system. Input message source sequence M equals to M1, M2, and etc. M is binary digit, which is in bit. The I is the time index. Will transform to unique code word U equals to G bracket M after undergoes convolution encode. The most popular from the several methods used for representing a convolution code encoder will be connection pictorial, connection vectors or polynomials, state diagram, tree diagram, and trellis diagram.
Hi, my name is Tam Jin Xian. I will present about the connection representation. The connection representation will be represented by the shift register, which convolutional encoder with constraint length k equal to 3, n equal to 2 modulo 2 adders with the code rate k over n half. The choice of connection between adders and stage of register give rise to the characteristics of the code. Any change in choice of connection results in a different code. Convolutional code has no particular block size, often falls into a block structure by periodic truncation. Number of 0 bits are needed to add to the end of the input data sequence, thus creating the encoding shift register of data feeds. Next, the shift register, which represents the connection pictorial, shows that with the example of k equal to 3, r equal to 2, and the generator vectors are chosen as 111 and 101. Discrete sampling times are labeled n. The data stream enters on the left and the present bit at time n, the most recent bit n-1 and the next earliest bit at n-2 occupy the shift register. Two parity bits are switched out in the interval between n and n-1 from the upper adder and then the lower one. When the next bit arrives, the shift register moves its content to the right. The k-1 earlier bits, in this case 2, determine the state of the encoder. They are shown in gray in the figure. There are 2 to the power of k-1 and k-1 states. For each encoder state, there are 2 possibilities of output code bits, depending on whether the input bit is 0 or 1. The progression of states in time then are a function of the data stream. Next, the connection vector is same as the connection pictorial in the connection representation, but it specifies a set of n connection vector, one of each of the n modulo 2 adders. Each vector has dimension k and describes the connection of the encoding shift register to the modulo 2 adder. 1 is represent the connection corresponding stage to the modulo 2 adder, and 0 is no connection between stage and modulo 2 adder. As example, connection vector for upper U1 is equal to 111, lower U2 is equal to 101, and the M is equal to 101 is convolutionally encoded. 3 message bits are inputted, one at each in T1, T2, T3, which is each in the 3 times. Subsequently, k-1 equal 2 zeros are inputted at time t4, t5 to flush the register. Thus, ensure that the tail end of the message is shifted the full length of the register. Output sequence is 11100001011. To flush the message from the encoder requires k-1 flush bits. New message can be entered at time t6 when 0 input is shown at time t6, which the reader verified that the flushing is completed at time t5. Thank you.
Now I will present the polynomial representation. Encoder connections are characterized by a generator polynomial, represent a convolution encoder with a set of n generator polynomial, each of the n modulo 2 adders. Each polynomial is of degree k-1 or less. Coefficient of each term in k-1 degree polynomial is either 1, which is means connected, or 0, or which is means no connection between shift register and modulo 2 adder. As an example, generator polynomial g1x is equal to 1 plus x squared in output connection. G1x is equal to 1 plus x squared. This means it's lower connection. Output sequence ux is equal to m bracket x g1x interface with mx g2x. The output polynomial ux can be found with input message m equals to 101 polynomial mx is equal to 1 plus x squared. Beside is the equation. Next is a stack diagram, and it's also represented by finite state machine, which is the smallest amount of information that can predict the output of the machine with current input provided. Beside diagram is the state diagram. The state diagram is also shows encoder with red is equal to 1 over 2, k is equal to 3. Each state is shown inside a circle, and the change from one state to another is shown by an arrow. Identified by the input bit, output code bit. Encoding can be done by relatively simple hardware. The decoder estimates the data string based on the received code bit sequence and knowledge of the encoder state diagram. Next is the tree diagram. Beside the diagram is about the tree diagram. The tree diagram adds the dimension of time to the state diagram, as it cannot easily used for tracking the encoder transition as a function of time, since the state diagram cannot represent time history. If the input is equal to 0, associated branch word is found by moving to the next rightmost branch in the outward direction. If the input is 1, the branch word is found by moving the next rightmost branch in the downward direction. Assuming initial contents of the encoder is all 0. The diagram shows if first input bit is 0, output branch word is 0. If first input bit is 1, the output branch word is 11. Diagram shows input sequence 11011 traced to output code word sequence is equal to 11010 10001. Thank you.
My name is Hong Zhangle, and now I would like to present about the terrace diagram. The terrace diagram is about the progression of state in time for all message streams can be shown by a terrace diagram, which is a continuation of our previous example. Terrace diagram can be used in convolutional encoding and decoding. And the theories require 2 power of k minus 1 node to represent the possible encoder state. After that, I will present about the theories sender's view. At the sender, transmitted bit trace a unite single path and branch through the theories. Like the example from the diagram below is transmitted data bit is 1011 and the recover transmit bit are equal to the recover path. Next, lastly, I would like to present about the conclusion. A convolution encoder is a finite state machine. An encoder with n binary cell will have 2 power of n states. The most commonly known graphical representation of a chord is the trellis representation. A chord trellis diagram is simple and edge label directed graph in which every path represented a chord sequence. This representation has resulted in a wide range of applications of convolution code for error control in digital communication. And the widely algorithm for decoding a bit stream that has been encoded use forward error correction based on a convolution code. That's all for our presentation. Thank you.
Thank you.